The Pacific Ocean, 3.2 million square miles, 90% of it deeper than 2 miles. A surface so featureless that finding a single object on it, even an object the size of 4 city blocks, is one of the hardest intelligence problems in modern warfare. This satellite does not care about politics. It does not care about treaties. It transmits microwave pulses downward at the speed of light, receives their reflections and builds pictures. Not photographs, something more precise. Radar images, even through clouds, even at night, even from space. Somewhere on that black ocean surface, something is moving, something enormous, something that generates a wake 3 miles long and a thermal signature visible from orbit today. We examine a scenario that strategic planners at the Pentagon have war-gamed more than 500 times in the last decade. A scenario that keeps admirals awake at 3 in the morning. What happens when the carrier is found? What happens when the missile is launched? What happens when the most expensive, most powerful, most defended warship in human history meets 25 years of Chinese engineering aimed at a single purpose, killing it? This is not science fiction. Every system in this film is real. Every number has been published. Every physics equation is verified. This is Carrier Killer. Before a missile can be launched, the target must be found. Before the target can be found, it must be watched. And before it can be watched, someone must build the architecture to watch it. China has spent 30 years building exactly that architecture. They call it, unofficially, the kill web. The backbone is orbital, China's Yaogan satellite constellation, which loosely translates as remote sensing, is comprised of more than 100 satellites in various orbits. Within this constellation, the synthetic aperture radar variants are the most militarily significant. Unlike optical cameras, SAR systems emit their own microwave radiation. They do not need sunlight. They penetrate clouds. They function at all hours. And crucially, their resolution has improved to roughly 1 meter. 1 meter from 500 kilometers up. That means the radar can distinguish individual aircraft on a carrier's flight deck. But satellites have a fundamental weakness. They are predictable. The carrier's navigation officer knows exactly when a Chinese reconnaissance satellite will pass overhead. The orbital mechanics are published in civilian databases. For years, US carriers could time their high-speed transits and emissions to avoid overflight windows. They called this MCON, emissions control. Go quiet, change course, be somewhere else when the eye in the sky blinks. China's answer was to build more eyes. Over-the-horizon backscatter radar, OTHB. These are ground-based systems that bounce high-frequency radio waves off the ionosphere, the electrically charged upper atmosphere, allowing them to illuminate targets beyond the curvature of the Earth. China has deployed multiple OTH systems along its eastern coastline. Their range, 3,000 kilometers. Their coverage, most of the western Pacific. OTH radar cannot give you a 1-meter photograph. What it can give you is a persistent broad-area movement picture, a large, fast-moving surface contact, generating a consistent radar cross-section, moving at 20-something knots. That is not a weather system. That is a carrier strike group. The geometry of the kill web works like this. OTH provides the cue. The satellite provides the confirmation. A third intelligence stream, signals intelligence, SIGINT, detecting the carrier's own radar and communication emissions, provides the track. 3 independent systems, 3 overlapping data streams, fused in real time at the People's Liberation Army Rocket Force Targeting Center in the Hebei province. The U.S. Navy is not unaware of this problem. The Ford and her escorts maintain a combat information center running continuously, monitoring for surveillance emissions. Electronic warfare officers track every radar frequency in their environment. When a Yaogan SAR pass is detected, identified by its characteristic pulse frequency, the carrier's commanding officer is notified immediately. The question, the one that gives planners nightmares, is this. What if the satellite doesn't reveal itself? What if the OTH track is good enough? What if SIGINT is all they need? In our scenario, the answer is, on this day, in this ocean, under these cloud conditions, the kill web closes. The ford is found. A targeting solution, a precise latitude, longitude, course, and speed, is transmitted from the satellite ground station to the PLARF command authority. The decision is made. The DF-21D Dongfeng, East Wind, the missile that fundamentally changed the strategic calculus of Pacific naval power. The DF-21D is classified as a medium-range ballistic missile. The D variant is the one specifically engineered for naval targeting. Its distinguishing feature is not its range. It is not its speed. It is the MARV, the maneuverable re-entry vehicle, the warhead that sits atop the missile and, upon re-entry into the atmosphere, can actively maneuver to track and intercept a moving target. A ship moving at 28 knots travels roughly half a mile per minute. At a range of 1,500 kilometers, a ballistic missile is in flight for approximately 10 to 12 minutes. In that time, the carrier moves roughly 5 to 7 miles from its position at launch. A conventional ballistic missile, a fixed trajectory weapon, would miss. The MARV is the answer to that problem. Somewhere in the Philippine Sea, the USS Gerald R. Ford's SPY-6 radar detects something. At 65,000 feet and climbing, a ballistic track appears in the CIC's vertical display. The system classifies it automatically. TBM, Theater Ballistic Missile. The time of flight calculation runs 9 minutes to impact. The battle group is already responding. The Fords escorting cruisers and destroyers, equipped with the Aegis Combat System, are already tracking the missile. Aegis is a marvel of systems engineering. Its SPY-1D phased array radar can track more than 200 targets simultaneously. Its engagement doctrine is layered, integrated, and, in theory, formidable. The senior escort vessel, an Arleigh Burke-class guided missile destroyer, has a firing solution. The SM-3 Block 2A is the most capable interceptor in the U.S. Navy's arsenal against ballistic missiles. It does not explode. Let that sink in. It kills by hitting. A roughly 70-kilogram kill vehicle, the kinetic kill vehicle, is launched into space on a rocket, guided by onboard sensors and data links from Aegis, and directed to physically collide with the incoming warhead at a combined closing speed, measured in kilometers per second. It is, in essence, the world's most expensive and sophisticated game of billiards, in space, with targets moving at thousands of meters per second. In the PLARF targeting center, this launch is detected. Satellites watch the exhaust plume. The DF-21D's MARV, still ascending, receives a data link update. New trajectory options are computed. The MARV has maneuvering capability, modest but real. It can alter its predicted impact point by tens of kilometers. It does so now, not to evade, but to adjust for the carrier's latest position update. The SM-3 kills its intercept solution and must recalculate. The window is closing. At these velocities, seconds translate to hundreds of kilometers. The Aegis computer calculates a new intercept point. The KKV maneuvers again. The kinetic physics of this engagement are staggering. Two objects, the warhead and the interceptor, are closing on each other at a combined velocity of perhaps 8 to 10 kilometers per second. The entire engagement window, from radar acquisition to intercept attempt, lasts approximately 90 seconds. Any computational error, any sensor noise, any vibration in the guidance system, any underestimation of the warhead's maneuver capability, and the interceptor misses. In this scenario, built on the realistic assessment of defense analysts who have reviewed this problem in unclassified settings, the SM-3 misses. The MARV is now committed to re-entry, aimed at a carrier it has never seen and cannot yet acquire, riding a trajectory shaped by mathematics and satellite imagery that is already 8 minutes old. This is where the terminal guidance system earns its price tag. At the top of the arc, approximately 400 kilometers above the ocean surface, the MARV begins its re-entry. The atmosphere thickens around it. Friction builds at velocities exceeding 8 kilometers per second. Air is not air anymore. It becomes a medium that the warhead compresses and ionizes. The temperature at the leading edge of the warhead's heat shield climbs past 8,000 degrees Celsius, hotter than the surface of the sun. This plasma sheath creates a phenomenon that no radar engineer has fully solved. Radio waves, the lifeblood of radar tracking and missile guidance, cannot penetrate ionized plasma efficiently. The frequencies are absorbed or scattered. During the thickest part of re-entry, the MARV experiences what engineers call a radio blackout. The seeker head inside the warhead, the radar that will eventually be used to find the carrier, is temporarily blinded. The Aegis radar tracking the descending warhead experiences degraded returns. The track quality drops. This blackout phase lasts perhaps 60 seconds. In 60 seconds, the MARV falls from 70 kilometers altitude to perhaps 20 kilometers altitude. In 60 seconds, it covers roughly 400 kilometers of horizontal and vertical distance. When the plasma dissipates and the seeker head reactivates, it has approximately 30 seconds of autonomous homing time before impact. The Aegis operators aboard the escorting destroyer have not been idle during the re-entry phase. They have been queuing their last-ditch interceptor, the SM-6. The SM-6 is a capable, versatile missile. Against a cruise missile, against an anti-ship missile traveling at Mach 2 or 3, it is lethal. Against a Mach 10 ballistic re-entry vehicle in the terminal phase, the mathematics become brutal. The interceptor must be in exactly the right place, at exactly the right time. The engagement window, the brief geometric window where a hit is physically possible, given the relative velocities, is measured in seconds. 2 SM-6 missiles are fired. Both are guided by Aegis, which has reacquired the track as the plasma blackout clears. The target is falling at roughly 3 kilometers per second, Mach 10. The SM-6 climbs at roughly Mach 3.5. The closing geometry is unforgiving. Here is where Hollywood would save the day. The warhead explodes in a fireball. The ship is safe. The crew cheers. The admiral nods gravely. Here is what physics says. The MARV weighs approximately 1,000 kilograms. Its kinetic energy at Mach 10, using the basic formula Ke equals 1/2 times mass times velocity squared, is staggering. A 1,000 kilogram object moving at approximately 3,400 meters per second carries kinetic energy of roughly 5.8 gigajoules. For reference, 1 ton of TNT releases approximately 4.2 gigajoules. This warhead, before its explosive filler even detonates, carries the kinetic energy equivalent of nearly 1.5 tons of TNT in momentum alone. The Phalanx CIWS, the close-in weapon system, the 20mm rotary cannon that is literally the last resort, fires at a rate of 4,500 rounds per minute. It is a superbly engineered weapon. Against a low-flying subsonic cruise missile, it can be decisive. Against the debris field of a fragmented hypersonic warhead, dozens of fragments each the size of a car engine, each moving faster than a rifle bullet. It is cosmetically optimistic. The shrapnel cloud alone, arriving at Mach 8, would strip radar antennas, shred aircraft on the deck, kill personnel, and crater steel. The MARV's seeker head has now acquired the carrier. 30 seconds. It can see the massive radar return of an 85,000-ton ship. It adjusts. Small final corrections. The terminal dive angle is calculated to maximize penetration. Nearly vertical, to punch through the flight deck and into the densely packed hangar bay below. It takes the warhead 11 milliseconds to travel from aircraft altitude to the flight deck. 11 milliseconds. The flight deck of a Nimitz or Ford-class carrier is made of high-strength steel plate, approximately 60 millimeters thick in the flight deck proper. The MARV's kinetic energy 5.8 gigajoules of it, arrives in a focused 1.4 meter diameter contact zone. The deck does not stop it. The deck does not slow it appreciably. The penetrator punches through the steel like a hot iron through parchment. The first space the penetrator encounters below the deck is the Electromagnetic Aircraft Launch System Bay, the EMALS. The Ford-class carrier replaced the old steam catapults with EMALS, a linear induction motor system that accelerates aircraft to flying speed using electromagnetic force. It is a sophisticated, enormously expensive system. It is also, at the moment of impact, a room full of high-voltage superconducting components, power conversion electronics, and hydraulic machinery. The kinetic penetrator vaporizes it, not damages it, vaporizes it. Below the EMALS bay is the hangar deck. 35 to 40 aircraft, F/A, 18S, F-35CS, E-2D Hawkeyes are staged there, some fueled, some armed, awaiting flight operations. The force of the impact, combined with the conventional explosive payload of the warhead detonating in the enclosed space of the hangar bay, converts this space into a furnace. Now let us be precise about what has happened and what has not happened. The USS Gerald R. Ford has not sunk. It will not sink from this strike. Its designers gave it 2,600 compartments. Its nuclear reactors are protected behind layers of structure deep in the ship's keel. Its propulsion, 2 Bechtel A-1B reactors driving 4 shafts, is intact. The ship is moving. The ship is not listing significantly. A crew of roughly 4,500 trained personnel is doing exactly what they have drilled to do, containing the damage. But the USS Gerald R. Ford can no longer launch or recover aircraft. Its forward catapults are destroyed. Its flight deck has a 12-meter hole in it. The aft catapults may be functional, but the fire, now spreading to secondary fuels and ordnance, makes flight operations impossible. The aircraft on deck are becoming flying bombs. The ship survives. The carrier air wing, the actual instrument of American power projection, is dead. In the language of military strategy, this is called a mission kill. The asset exists. The asset cannot perform its mission for the cost of 1 missile, and the real cost of a DF-21D is estimated at somewhere between $5 and $10 million. China has removed from the operational equation an asset that costs $13 billion to build and roughly $1 billion per year to operate. The geopolitical clock starts the moment the Ford's flight operations are confirmed non-functional. The other carriers in the Pacific Fleet, USS Theodore Roosevelt, USS Ronald Reagan, are immediately repositioned. They move to ranges outside the DF-21D's estimated operational envelope, which means they are no longer close enough to provide meaningful air support to any conflict in the first island chain. Taiwan, the Senkakus, the South China Sea, the geographic buffer zone that Chinese planners designed, the DF-21D, to enforce the anti-access/area denial zone, a 2/AD, has been validated. In a single afternoon, the tactical map of the Western Pacific has changed. The USS Gerald R. Ford will not sink. She will make port, Pearl Harbor, or possibly Guam, escorted by her strike group, burning some fires, managing others. She will be repaired. In 6 to 18 months, she will sail again. The United States of America has not lost a carrier. It has never lost a carrier since World War II. But for those 6 to 18 months in the waters where the DF-21D can range, there will be one fewer carrier, one fewer floating airfield, one fewer symbol of American dominance of the sea, and the strategic lesson, the lesson broadcast to every Navy, every Air Force, every decision maker in Tokyo, in Taipei, in Manila, in Seoul, is this: it can be done. This is the fundamental tension at the core of 21st century naval power. The carrier is not obsolete. It remains the most versatile and capable power projection platform ever built. But for the first time since the 1940s, the carrier is not invulnerable. And the difference between invulnerable and merely formidably defended, that gap, is the gap in which wars begin. The engineers who designed the DF-21D understood physics and patience. They understood that the most powerful navy in the world could not be beaten by building a more powerful navy. They could be threatened, strategically threatened, by building one very fast, very accurate, very difficult to stop arrow and aiming it at the single platform upon which American naval dominance depended. The answer to the DF-21D is not a better CIWS. It is not a faster interceptor alone. The answer, according to the strategists who have thought hardest about this, lies in distributed lethality. More platforms, smaller targets, decentralized power. The answer lies in long-range unmanned strike, in submarines, in networks that don't depend on a single ship. But that answer takes time, it takes budget, it takes doctrine change, and doctrine changes slowly, because carriers have been the answer for 80 years. It is very hard to argue against something that has worked for 80 years. Until one Tuesday afternoon in the Philippine Sea, when a $5 million missile lands on a $13 billion ship, and the most powerful navy in history learns that physics does not care about tradition. The East Wind did not sink a carrier. It didn't have to.